All right, any questions before we get back into area between curves?
All right.
All right, so now I want to find the area enclosed between the curves defined with these two equations. How should we get started?
Y squared is y squared.
Okay, so Saul would like to do something about the y squared because y is not a function of x. Do I need y to be a function of x to find area between curves?
If you do the function of x, I mean, sorry, like, make it in terms of x.
Yeah, I mean, I know what you mean. It is in terms of x. I think you want to make it in terms of y.
Yeah.
Or solve for x. So in general, no, we don't need to have functions of x. I think we did one, right? Right? Yeah, okay. You can have x being a function of y and still do this. We did one like that early last time. We could also do this as a function of x. I think we need to break it up into two integrals to do that. But if you'd like, I mean, I'll leave it up to the majority rule here. Do you want to keep this as is and do as a function? X is a function of y, or y is a function of x? Someone has to vote.
Well, if we did a y, wouldn't it be like, we would have to do plus and then minus?
You would have to do two different integrals because you have two different functions that basically comprise this curve here. So y equals plus or minus the square root of 2x plus 6. We can do that. You would rather not? Okay. So if we would rather not do it that way, then yes, we have to basically treat these as basically I want x to be a function of y. So I'll call this f of y. I'll call this g of y. 1/2 y squared minus 6, I believe. So if we want to do this where x is a function of y, I think we can get away with only doing one integral. I think that's a good first step. What else should we do?
Find the points where they intersect.
Okay, I should, if I want to find the area enclosed, I need to know, where to integrate over. So I want to find the bounds. How do I find the bounds?
You can set them equal to each
I can set them equal to each other. Or I propose this. So I know that y equals x minus 1, right? And I know something about y squared. So I'll do this. X minus 1 squared equals 2x plus 6. X squared minus 2x plus 1. So I think that should help us find our bounds. Does this factor cleanly? I think it does. Okay, so I think we have the two functions that describe the area between our curves. We have the bounds of the integral we're going to set up. Now, go ahead, Colin.
Are those x bounds and we're solving for like?
Yeah, those are x bounds. So yeah, we don't really have the bounds, but we can get them, right? How do we get the bounds from those x values?
Plugging them into the.
Which one?
Right, doesn't matter.
It doesn't matter. So which one would you rather do? Yeah, it's probably a better call. So I know that y equals -1 minus 1, so that's -2, and y equals 5 minus 1, so that's 4. So now I think I have my bounds for my integral that's going to have y as the independent variable. Are we now ready to set up that integral? So this should be the integral on what bounds? -2 to 4. And what is the function we're integrating?
We can find which.
Yeah, so we need to find which one is it really upper this time? So remember, we're doing the function, basically we're looking at functions that are expressed in y. So basically we're comparing x values. So we're not looking for the upper function first, we're looking for basically the rightmost function. How can we tell which one of these functions is on the right within -2 to 4? So here's what's really useful about that's quadratic we just solved. We found basically the 2 points where these functions, these curves meet, right? But the other kind of subtle thing that's also very important is we've proved that it doesn't happen anywhere else. So here's what you know is between -2 and 4, one of those functions is to the right the entire time, because I found the only 2 places where they meet. So basically one has to be greater than the other, like within that interval, and it's not going to change. So we can just take any point on that interval as a test, and we can guarantee that whatever function is greater at that one point will be greater everywhere. Does that make sense, or I can try again? So now I can just choose a convenient value for y. 0 is probably the most convenient one. So I called these things f and g up here. So let's do this. Let's not set up the integral yet. What is f of 0? That should be 0 plus 1, so 1. What is g of 0? That should be 1/2 0 squared minus 6. So -6. So I think I can say with certainty that f is the greater function on that interval, right? So knowing that, I can set up this integral from -2 to 4 of f minus g. So go ahead.
Was the 1/2 in g of x up there applied to the entire thing or just the?
I mean, yeah, that's a good catch. It should be. Thank you. So I got the right conclusion for the wrong reason. So yeah, it should be -12. So now I'm subtracting y plus 1 minus 1/2. What's that? Yeah, it is. I need a weekend. You know what? Let's just distribute this thing so that doesn't happen anymore. Y squared minus 3. So let's pause here. I mean, I think the more important part of this, maybe at least the new part of this, is setting up the integral. I believe wholeheartedly you all can evaluate the integral, but let's make sure that we're okay with how it got defined. If we're okay, let's go ahead and keep going. What do you want to do now? Integrate. All right. If I integrate, what does that become? Okay, y squared over 2 plus y minus y cubed over 6 minus 3y. We still have to have this parentheses here. So many of you are probably, some of you are probably wondering why we didn't simplify first. You can. Can also do it now. So why does that y squared over y? Y squared over 2. So y squared over 2. Collect the y and the 3y, that becomes minus 2y. minus y cubed over 6. So I think the integral's done and simplified as much as we can do it. Now what? Evaluate. So evaluating at 4, y 4 squared over 2 should be 8. Minus 8. Minus 64 over 6, so 32 over 3. Minus all this. 2. Plus 4. Is this gonna come out negative?
Well, is that 3 supposed to be positive? That 3y shouldn't it be plus 1?
Right here?
Yeah, like so it's a double negative, so when you simplify it, shouldn't it be 4y instead of negative 2y?
Yeah, thank you. Someone want to take over? So let's try this again. So 8 plus 16. Okay. Four cubed is 64, right? Yeah. Okay, do we like it now? All right, so this should come out positive. So whole numbers first. 24 plus 6 will be 30. Minus 36 thirds, which is 12. I got a final result of 18. Okay. Any questions? All right. Go ahead. Oh, sorry. Water, not question. All right. Last one for you. So we've got some information. So I want to find that blue shaded area. How do we go about doing that? Okay. What are the bounds? Negative 3 and 0. Okay, so we know the bounds are going to be given by these points, right? Negative 3, 3, and then this is the origin. But I think if we're gonna, before we talk about what the bounds are, I think we have to answer another question first. What question is that? Yeah, so we like that's good. That is going to govern what the bounds look like. We can only deal with one variable, so let's figure out what variable that should be. Why should it be y?
Because you're doing x and have to deal with square roots.
Right. Right. So yeah, I mean we could do this in x. That would require multiple integrals, but it's absolutely doable. If we do it in y though, another way to look at it is this. If we do it in y, we have to figure out what the right hand curve and the left hand curve are, right? Over whatever our bounds would be. So let's say this. Let's say we're going to go forward and do this in y. If we do this in y, what are the bounds? 0 to 3, right? Over the interval 0, 3, the y interval 0, 3. Is the right hand curve the same curve? It should be for that whole interval, the right hand curve should be consistent. And the left hand curve, is that consistently the same thing? Okay, yeah, that's true. So let's look the other way. What if I wanted to set this up for x? Then the bounds would be negative 3 to 0, right? If I'm looking in the x direction, or sorry, yeah, if I'm using x as my variable to integrate on, I'm not looking for right hand curve and left hand curve. I'm looking for upper and lower, right? Is the upper curve consistent over that X interval? Colin?
I had a question, I think on the web work, there was a similar problem to this,
Uh-huh.
to find the area bounded by the curve, would you actually not use -3 because it cuts off part of that parabola?
Oh, yeah, you're right. The bounds would be further left.
So
Yeah, we'd have to figure out what that point is. So, yeah, it would not be -3. It would be. Gonna figure it out by staring at it a little bit. I think it'd be -4. But whatever it is, it's certainly left, right? So over that interval from -4 to 0, is the upper curve consistently the same curve? I don't think so. I think something happens here. So to the left of that dashed line I just did, you're really just finding the area like kind of tucked in that blue curve there. But if you go to the right of that, you have to look at the area underneath something different, a different curve, which means you can't use the same integral to handle that. You have to use at least 2. I think it might even be 3. So I think a wiser choice is, yes, to go from 0 to 3. Of what? What is the integral we're going to do? Or what's the integrand?
Y squared.
Why is it 2y minus y squared first?
Right.
That's the right function. Subtracted by y squared minus 4y.
I have a question,
Yeah,
like, if, what is the area under the curve, just look for like the blue one? Is it like this area or
Oh,
is it
yes.
like everything else?
that's a good question. So if you like, let's say we. So let me write down what I think you're asking. You can correct me if it's not what you're really getting after. So let's try to put the pink curve out of our mind. And if I integrate, I'm not even gonna worry about the bounds for now. If I just integrate y squared minus 4y from y equals 0 to y equals 4, what does that do? So I think being at least all the times I've looked at area under a single curve with you all, it's always been in terms of x, right? So this time we're looking in terms of y. So what area, if I were to just to do that bottom integral that I wrote down, what would that find?
Would it just be like above X, like that part of the thing? Like not the bottom? Not the negative side?
Okay. Oh, would it just be this?
No, like the whole thing, not the negative side of the Y, I meant. But I don't know.
Yeah, I'm not even sure I'm understanding what you're saying.
All of them. Well, like the pink, the shaded region, but also on top of the shaded region, that area right there.
Like up here.
Yes.
I don't think so, because I think we're still trying to treat this as if it's an integral in x. So let's use an analog here. What if let's go back to one that actually is easier to define.
Like those I understand because it's like under the current, you can see it under, but it's in the other one, like it's under, but then there's another line that's like.
Right, and that's the point I'm trying to get to, is that the question is no longer under the curve anymore. Because, so if I were to integrate one of these, essentially what I'm doing is, so let's call this y1, the red one, and y2, the blue one. If I integrate y1, which is really a function in x, dx, that's going to find me the area from the curve down to the x-axis, right? So basically from all the y values starting at the curve down to y equals 0. Does that make sense?
Yeah.
So if we tilt that, metaphorically speaking, tilt that to look at something in the other variable, you're not finding the area above the x-axis, you're finding the area to the right of the y-axis. you're finding the area from your greatest X values down to X equals 0. So basically what that's going to find is, and it shouldn't even be 0 to 4. Like if I'm just trying to find, I would have to figure out what that Y value right there is. And I would find that area right there. So instead of finding the area above Y equals 0, I'm trying to find that integral would find me the area right of X equals 0.
How do you get the other?
The rest of the blue one here?
Yeah.
That's what I was about to set up in the X direction. So that's why you need the other curve. Is because if you just integrate under one curve, essentially what you're doing is this. I'm finding the area between two curves. This is the right curve, and the left curve is this. So basically, the area between the pink parabola and Y equals 0, which is, no, sorry, X equals 0, which is the Y axis. But if we want to find all the area behind it, we have to compare the pink curve to the blue curve. So basically, if you think this back to Riemann sums, the integral that only deals with one curve is finding these rectangles. But if I subtract the other curve from it, then the rectangles I'm actually getting extend all the way back, which is what we really want to do.
So when did you add this? Or no?
We do, because I mean all the values behind the y-axis are negative, right? So when you subtract them, they end up becoming a net positive again. All right, so any more questions about that scenario? All right, now it's good. It's good to think about what these integrals are actually doing, especially when you start using them in the variable you're not used to using them on. All right, so we set up the integral. Now what would you like to do with it? Okay. Do you want to simplify first, or do we not like doing that? Okay, let's do that. We didn't do that last time, so let's do it this time. So from 0 to 3 of 2y plus 4y is 6y. Negative y squared minus y squared is minus 2y squared. And that's it, Eric. Now I think we can integrate. So integral of 6y is 3y squared. Integral of 2y squared is 2/3 y cubed. From 0 to 3. So 3 times 9 is 27. 3 cubed is 27. 2/3 of that is 18. And then I think this is just, yeah. Final area of 9. Okay. Any questions about area between curves before we move into three-dimensional stuff? Okay, so done a lot of things with integration and area. Now we're going to use integrals to talk about volume. So does not really make sense unless we do something with the areas we talk about to make them three-dimensional. So let's talk about how we're going to do that. So there are a few different ways to find the area, find the volume indicated by a function. The first one we're going to talk about is this disk method. Has anyone seen this before? Okay, so why do we call it the disk method? You spin it around. Yeah, you spin it. So that's, I mean, you can spin around either axis. First, we're going to talk about the x-axis. But yeah, basically, I'm going to take this two-dimensional area and we're gonna kind of extend the Riemann sum. So if I make rectangles here, rectangles are a very regular, predictable shape. If I were to take that little rectangle and revolve it around the x-axis, is going to make a disc, right? What shape is that disc going to have? Circle. I can't say circle. It's three-dimensional, right? Not sphere. It's a cylinder, right? Okay. Just making sure we all got the word. So yes, it's going to be a cylinder. Yeah. So if you look at a cylinder, which I don't have a good example of, but basically it does have circular bases, but it is not, in totality a circle. It has other dimensions we have to worry about, that'll be more clear when we look at other volumes or other ways to find volume. But yeah, we're going to basically split this two-dimensional area into rectangles and revolve those rectangles around an axis to make a whole bunch of cylindrical discs. Can we find the volume of a cylinder? Do we remember how to do that? So let me try to draw a bad cylinder here. It's actually not bad. So it does have a circular base, which should give you a bit of a clue as to how to find its volume. Geometrically, do you remember what a prism is by definition? A prism is a shape that, like, no matter where you slice it, it always has the same cross section. So a cylinder is a prism because no matter how tall it is, you can always slice it and it'll have the same size circle that you cut through, right? So because of that, it's a prism. And the way I find the volume of prisms is by multiplying how tall they are by whatever the area is, because the area that you get by cutting through it is consistent. What is the base? How do I find the area of a base of one of these things? So this volume of a cylinder is pi times r squared times height. So this is essentially how we're going to use integration to find volumes, is using the fact that I know what the volume of a cylinder is, and I'm going to treat this volume here as just a bunch of really thin cylinders. Take all their volumes and add them all together. So that's the rationale behind kind of how this is going to work. Any questions so far with that? Before we get into a concrete example, does anybody have any questions about kind of the game as I've defined it? Okay, so let's look at a relatively simple one. So I have a constant function here essentially. So this is f of x equals 4. And I want to find the volume of this thing if I revolve it around the x-axis. So if I take a rectangle and I think about revolving that around the x-axis, this rectangle will have a height. Height means kind of weird to think of height because it's resting on its side, but it has that thickness of dx. So here's what I want to talk about. I want to find the volume of cylinders, which is pi times r squared times height. But how do I turn this into an integral? So let's talk about that. Really what we're going to do is, pi is a constant. The radius in general is going to be a function of basically wherever this is. Basically, wherever I draw the rectangle, the radius might be different because I might be further from the x-axis or closer to it. So I want to indicate that by saying that my radius is a function of x. What is my height for all these rectangles going to be? That's going to be dx, right? So imagine that I was coordinated enough to make these all the same thickness. That's going to be a constant dx, right? So essentially, this is the integral I'm setting up. The volume is equal to the integral of pi times the radius squared dx. So basically, even though I kind of am building this up for a specific example, this thing is the disk method. This is generally how this works. If you're going to revolve around some horizontal line, I need to know what the radius is. So basically, how far, for any given x value, how far am I from the horizontal line I'm going to revolve this over? And basically, I'm going to find the volume of all those little cylinders I'm going to generate. So in this specific case, I want to revolve that horizontal line at y equals 4 around the x-axis. So can I define the radius for this example as a function of x? What is the radius here? Just constantly 4? Should be constantly 4. So I mean, I know we talked about like we're approximating this with cylinders, but this is a constant function. So if I wrap that around the x-axis, that should become a cylinder, right? If I revolve a rectangle. So if r of x equals 4, then I think my volume can be written this way. The volume is equal to the integral of pi times 4 squared dx. We're missing something. We're missing the bounds. 0 to 4. So I think that's a good setup for this integral. Not totally simplified yet, but any questions about what we've done so far? Okay. So now I would like to integrate 0 to 4 of 16 pi dx. What is that integral? 16 pi x from 0 to 4 should give me 64 pi. Is that the same volume if we would have just done this, using the canned geometric formula we would have got? Pi r squared h. You said the radius was 4, right? What is the height of this cylinder if I were to revolve that whole thing? Also 4, right? So that should be, yeah, they should come out to be equal. So in this case, we could have just used non-calculus means to find that volume, but trying to graduate up to more complex functions. Any questions on this first one? Okay, let's do another one we can kind of test with geometry. If I were to revolve this around the x-axis, what shape would that make? That's a cone. Do you remember how to find the volume of cones? It's essentially, and you might have seen a video before where basically if you take a cylinder of a certain height and radius and you take a cone of the same height and radius, you can fill it. You basically, the cylinder can fill up the cone 3 times. So volume of a cone is 1/3 pi r squared h. So we're going to use integration. But basically, this should come out to 64/3 pi, since that's exactly 1/3 of our last example. So let's make sure we get there. In general, to find volume using disks, if I integrate over the bounds, where my interval a to b of pi times the radius function squared dx, that should give us our volume. So how can we define the radius in this situation? So now if I draw rectangles at different places, they're going to have very different radii. So is there a way for me to define my volume here, or define my radius?
X.
Is it just x? Yeah, so this line right here is like the unit y equals x function. Slope of 1 goes with the origin. So because of that, can I say that R of X equals X? Okay, so if we say R of X equals X, then let's finish setting up this integral. The volume over what bounds? Should be 0 to 4 again. 0 to 4 of pi x squared dx. What is the integral of pi x squared?
X. X cubed over 3.
X cubed pi over 3. So here's one thing I'm going to point out, since I got very used to you all telling me to pull constants out of integrals. We can absolutely do that. So you don't have to, but if you'd rather not deal with it until the very end, that's fine. But for now, let's pull it out just to give you a different look. So the integral of x squared is x cubed over 3. Evaluated from 0 to 4. And that should give us 64 over 3 pi. Any questions? So now let's look at something a little different. So instead of me giving you a picture, I'm just giving a description. So I have a solid. Remember, all these solids we're going to talk about, we're going to generate them by taking some two-dimensional region, that area, and revolving it around some line. So now the thing I'm looking at is basically the area under the curve y equals radical x, and finding the volume that I get from that when I revolve it between x equals 0 and x equals 1. So any ideas how to proceed with this? Go ahead.
Well, we're given R of X and A and B in the equation, right? Well.
Or okay, what are all those things?
Well, R of X would be root X.
Okay.
And then A would be 0 and B would be 1.
Okay. So you're saying that basically the R of X is equal to what the function I told you, right? Okay. Do we agree with that? Right. So for all the cases we've looked at so far, that'll be identical. I don't want to say it always will be, but for now we can say that. Basically what's going on here is this square root function. I'm going to look at it from 0 to 1. So yeah, no matter where I draw these rectangles, the radius is basically going to be whatever the height of this function is minus the height of the x-axis, which is just 0. So because of that, I can set up my integral like this. The volume is equal to pi times the integral from 0 to 1 of radical x squared dx. So pi times the integral from 0 to 1 of x dx. Maybe I should pause here. Any questions about the setup of this integral? All right, so what should the volume be? What's the integral of x? Squared over 2. From 0 to 1, that should come out to pi over 2. Questions so far? We're good with volumes. Okay. All right, so let's tilt this on another axis. I want to rotate this around the y-axis. So the region bounded by y equals x cubed, y equals 8, and x equals 0. So what would y'all like to do to start just kind of organizing what's going on here? Remember, I'm changing the direction of rotation. Now we're going to change. We're going to revolve around the y-axis, a vertical line. Any suggestions? Would you like to look at it? Okay, so I mean, that is something, I don't know, I feel like, especially when you're dealing with things in higher dimensions than you're used to looking, drawing a picture could be useful, even if it's not super accurate, like I promise mine's not going to be. So what does this thing look like? Y equals x cubed. The cubic function sort of looks like this.
Bounds be the same,
What's that?
should the bounds be in the same, like, is y equals 8 and x equals 0?
Yeah, so y equals 8 is a horizontal line, right? So I've drawn all the things that we care about. So I have two horizontal lines that are bounding this region, right? All right, can we show? Basically, we're building up a two-dimensional area into a three-dimensional volume. Do we know what the area looks like? I think I worded this kind of vaguely. It should be bounded by the y-axis as well. Otherwise, there's no limit to how far left it goes.
Yeah.
The bounds.
We have a question on whether we should put the bounds in terms of y. Which means we're integrating in terms of y. Should we be integrating in terms of y? I think we need to. And here's why. Like, so right now, I mean, some of you might have seen other methods to find volumes, but right now the only means we have is this. Basically, we're treating these as cylindrical disks. So volume equals pi r squared height. What's going to dictate the radius for the way I want to do this? So I'm revolving around the y-axis. So if I'm going around the y-axis, what's going to dictate what the radius is of all these rectangles? The x values, right? Because now basically I'm not taking these vertically oriented rectangles, I'm taking these horizontally oriented rectangles. And now I'm going to wrap them around the y-axis to make these like flat, tuna can looking discs that are like stand the way you probably envision a cylinder standing up. So because of that, the radius is not going to be some function for y, it's going to be some function for x. So that's the first thing I want to write down, is the volume is going to be equal to pi times some integral, where radius is a function of y squared dy. So I should probably pause there. So are we okay with the changes that have to be made when we start looking at this as a function of y? All right, so can I keep defining this integral? What are the bounds? 0 to 8? We agree with that? So our bounds are going to be an interval of y. So yes, I agree that, basically, I told you that basically I want to bound this with the x-axis, which is y equals 0, and the y equals 8 line. So yeah, I believe my bounds are 0 to 8. What is the function we're actually integrating? Or what's the radius function? How'd you get the cube root of y?
Isolate x and then get number.
Right. So if I told you that, yeah, y equals x cubed, but that's like a function of x, I need to isolate x to get y equals cube root y. So yes, I agree, this should be. The cube root of y. So I believe that integral is, that setup so far is really good. So any questions about how we got there? Before we finish the week by evaluating it. Okay. Where should we go from here? Is that an integral you can do? What is the integral of cube root of y squared? I might encourage this before you get started. Y to the 2/3. What's the integral of y to the 2/3?
3/5.
I hear 3/5. Y to the 5/3. What is 8 to the 5/3 power? 32. Do we do that with a calculator or in our heads? So 3/5 times 32 minus 3/5 times 0. That 96/5 pi. All right. First scan for errors. I think it's okay. I don't know if I want to start. Yeah, I don't want to start washer method in 2 minutes. Any questions here? We happy with volumes? Who hasn't never seen this before? Okay, so about half. Okay. So a couple different methods, a couple more methods of finding volumes we're going to talk about next week, but yeah, that about covers it for the disk method. But there are some more complicated cases we'll get into next time. All right, I'll give you a couple minutes early. Otherwise, if you want to stick around and talk to me, I'll be here for a little bit. Otherwise, I'll see you all next week.